audible now.
Sorry, ma'am. Just 1 minute, I'll share. Is my screen visible, ma'am?
Yes, it is.
Thank you. Thank you. So, hello everyone. Today I'll present uh, a few ideas on how to obtain aggregate flexibility curves for active distribution networks. So the concept originated, the basic motivation was the capability curves. The way the capability curves are obtained for synchronous machines, it is essentially the receiving end power circle diagram of a synchronous generator or synchronous machine connected via a transmission line to an infinite bus. First, we obtain the receiving end power circle diagram, and then we superimpose operating limits of the synchronous generator on that power circle diagram to get the capability curve. Now, on similar lines, let us replace this single machine with multiple resources, maybe a distributed generator or could be a battery. Let's replace the transmission line with a distribution network and the infinite bus with the transmission distribution interface bus. So on similar lines, we can also obtain a power circle diagram while considering these multiple resources connected via a distribution network to the interface bus. Such circle diagrams have been reported in one of our publications very recently, and then we can superimpose the operating limits of these resources as well as the operating limits of the distribution network on the diagram to get the aggregate flexibility curve. Now, since the main uh, topic of this presentation is flexibility curves, we will restrict ourselves to flexibility curves. The circle diagrams have been reported, and we can refer to this paper for further details. The capability curve for a synchronous machine, let's talk about it first, can be obtained by drawing the single line diagram of a synchronous generator connected by a transmission line and a transformer to an infinite bus. And then this is for the steady state. We need to draw the vector diagram, which is rotated and flipped to get this particular diagram. Here, these are not vectors, they represent magnitudes because they have been rotated and flipped just to get P and Q on the positive axis. Now, if you observe here, for a particular value of E is the internal voltage of the synchronous machine, the air gap voltage. For a particular value of E maximum, for fixed terminal voltage, of course, we get a circle. The loci of this particular point will be the green circle. For different values of E, we will get different circles. So this is how we get the circle diagram. Similarly, for different values of V, terminal voltage, and fixed values of E, we will get different red circles. But since our concern is to obtain the capability curve, let us draw one particular green circle for a maximum value of E, which corresponds to the maximum air gap voltage that can be obtained by maximizing the field current. So this green circle, let us say, represents the field limit of the synchronous machine. Similarly, the red circle, let us draw this, the loci of this point, red circle for a maximum value of armature current, which represents the armature limit of the synchronous machine. Similarly, PG max represents the turbine limit, and PG minimum represents the boiler limit. So the area which is enclosed by these limits, which is shown by this dotted curve, forms the capability curve of a synchronous machine. This is very important in practice, and the reference number 3 has very nicely explained the capability curve. Now, instead of performing this exercise, drawing the single line diagram, vector diagram, and then superimposing the limits, what we can do is let us solve an optimization problem where we maximize Sg, the complex power generated by the synchronous machine, for a fixed value of theta rated, subject to equality constraints, which are nothing but the power flow equations, which is another representation of these vector diagrams, the power balance equation, sorry, for the synchronous machine, and inequality constraints of the form E less than equal to E maximum, I less than equal to I maximum, delta less than equal to delta maximum, and all the other limits. So for a fixed value of theta rated, let us say theta rated equals to 0, I will reach this particular point. Similarly, for different values of theta rated, I can, let's say 30 degrees, I'll reach this point, 60 degrees, I'll reach this point, 90 degrees, I'll reach this point. We can get different points on this boundary, and we can connect those points to get this capability curve. This idea was presented in reference 4 and reference number 5. Now the same idea can be taken over to obtain flexibility curves, aggregate flexibility curves at the transmission distribution interface bus for an active distribution network. So the formulation uh, is like that. We maximize, let us say, the real power that can be injected at the transmission distribution interface bus from the distribution to transmission network, subject to the equality constraints, which are nothing but the power balance equations at each and every bus in the network. Inequality constraints, the first one represents the operating limits on voltage magnitudes. The second one represents the limits on real power output of different distributed generators. And the other inequality constraints are limits on current flowing through branches, the limits on angle difference across two ends of a branch, as well as the, let us say, the armature limit of a distributed generator. This represents the power output limit in terms of current limit of a distributed generator. So this particular equation, the last inequality constraints in G2 and the last inequality constraints in G1, they actually represent the capability curve of each individual distributed generator, which is essentially, very roughly, a semicircle for a DG and a complete circle for a battery. Now we solve this particular optimization problem using a sequential and constraint minimization technique. So the KKT conditions are written for this particular problem. They are perturbed so that we get interior point formulation, and it results in a system of equations which are expressed as f of z equals to 0. The mth iteration solution of this system of equation is obtained by using Newton's method. These are very popular techniques. You can refer the references for more details. Now, when we do this, we get one particular point on the curve, which is essentially, let's say for theta equals to 0 for synchronous machine, we get this particular point. Now we have to trace the entire curve. So what we can do is we can either repetitively solve an optimization problem, or we can use, what we have done is we have used a predictor corrector approach. We have sequentially traced the set of optimal solutions, all the optimal solutions on the boundary of the aggregate flexibility curve. So that curve, flexibility curve on P1 Q1 plane is traced starting from the first point that we obtained using this SUMD technique, using a predictor corrector approach, using uh, either P1 or Q1, let us say Q1 to begin with as the continuation parameter. So first we predict the solution by parameterizing the KKT conditions, determine the continuation parameter for the next predictor step, and then we correct the solution to get the optimal solution, which is adjacent, very adjacent to the previous solution. And we do this continuously. This predictor corrector exercise is performed continuously till the entire curve is traced. So what we tested our op continuation optimal power flow approach on two different test systems, 33 bus distribution network and 85 bus distribution network, by modifying, we modified them by placing various resources, distributed generators and batteries at different locations. Now these locations have not been chosen optimally because the main concern was of this research was to obtain an aggregate flexibility curve instead of determining the optimal location of these resources. We have assumed that the distribution networks are adequately equipped with distributed generators. These are the parameters and operating limits of parameters of distributed resources, their operating limits, and the network operating limits. Now, the results that we obtain are as follows. For the 33 bus distribution network, the aggregate flexibility curves were obtained for different loading conditions. Let us say for one per unit loading condition, this green curve we traced at on the P1Q1 plane. P1Q1 represents the real and reactive power injected from the distribution network to transmission network at the interface bus. So this curve represents on an aggregate without violating the static security of the network. That means without violating network operating limits, without violating the power output of distributed resources, this much real and reactive power can be realized at the transmission distribution interface. And for different loading levels, we change the load of uniformly and then obtain different curves. It can be observed that as the loading level increases, the curve flexibility curve tends to shift towards the positive P1Q1 axis. That means that we need to, as the load increases, the local resources are utilized more. The local resources are utilized more to supply the local loads, and hence the power that can be sent back. Well, I'm sorry if I have done a mistake. The positive P1Q1 represents the power drawn from the transmission network to the distribution network. Negative P1Q1 is the power which is sent back from the distribution network to the transmission network. So as the load of the net on the net distribution network increases, the power that can be sent back to the grid reduces because the local resources will be utilized to supply the local loads. And also, a family of such curves indicates that the surface which is formed is continuous. Surface which is formed by these curves for different loading conditions is continuous. Similarly, we obtain aggregate flexibility curves for 1 per unit loading with different output levels of distributed generators. However, the battery capacities have been kept intact. So similarly, what we can see is as the output level of distributed generator reduces, the curve again tends to shift towards the positive P1Q1 axis. This is because now you have less capability available or flexibility available in the distribution network to send power back to the grid. And it can be seen that there is always certain amount of flexibility retained because we have kept the battery capacities intact. We have not changed the capacity of the battery. That is why there is some region that will always remain within the aggregate flexibility curve. In the absence of that, this curve would have converged to the base case load flow solution of this particular network. Similarly, similar results were also obtained for a modified 85 bus distribution network as well as for a modified 85 bus distribution network for different loading conditions and for different output levels of the distributed generators. Thank you.
All right. So anybody have questions?
Yes, the thermal. Can you please clarify the thermal limit of?
Yeah, I have seen. Yeah, that's a very good thing. And yeah, I have seen your optimization, maybe, yeah, equations. But did you also consider thermal limit? It means, let's say, ampacity of the cable or your transformer limit. So do you have used that? I did not see anything.
So the first equation in inequality constraints G2 more than or equals to 0 limits the current which is flowing through each and every branch. So the IJ max is essentially the ampacity of every branch.
Okay. So how much difference from, let's say I have 2 generators, distributed generators, 3 something. So if I add all the P and all the Qs, how much difference from this curve and that?
Sir, if you add all the P and all the Q, essentially you should get a circle, a complete circle.
Okay.
But
so it
because
will be more accurate.
No, sir, it may not.
I know that is not the good answer. Yeah, if I only add the all P and Q, yeah, it's not correct. I know.
Absolutely.
So it's just the very straightforward, let's say,
Yes,
answer. But that's
absolutely.
why I asked that thermal limit, another thing. So
Yes.
what is the application of this one? Where I can use that?
So this
So let's
curve,
say,
yes,
if I have this curve, where I can use that? Those.
as a distribution system operator or as a distribution network operator, what I can do is instead of sharing any more information with the operators in the higher level of hierarchy, what I can do is I can share such curves, and then the TSO or the ISO can do the scheduling and dispatch without any much. uh, I'm not sharing any information with him, but I'm sharing everything that he needs for scheduling and dispatch. So the privacy as a DSO or DNO is respected, and the scheduling and dispatch by the system operator in the higher level of hierarchy also ensures that the network in the lower level is also secure. That is where such curves can be used. They can be shared without risk of privacy.
I don't understand this part, because if I want to dispatch optimum dispatch, then I need to run optimum dispatch, right? If
Yes,
I
sir.
give this curve, does it provide the optimum dispatch? This is just the total, how much P and Q I can. This is the capability curve, right? This total capability curve. Just you
Absolutely.
write aggregated
Absolutely.
of
Absolutely.
it does not give
Yes, I need.
me that minimum dispatch,
No,
minimum
sir.
cost dispatch. Yeah, go ahead, please. So how about optimization? You meant I have seen you have solved the unbalanced also non-linear optimization, right? And how long it takes, and does it always converts for the big system?
Am I audible? Hello?
Yes, you are.
Yes. Yes. Yes, of course, as a distribution system operator, network operator, I need to do the optimization exercise on my own. That's true, sir. But the power that I can draw from the interface, from the transmission network, that will be given to me by the system operator in the higher level of hierarchy. So only that information will be shared. Of course, I have to do my own optimization exercise, or essentially I have to, what I can say, desegregate again. Let us say I get 2 plus 3j that the TSO in the higher level of hierarchy shares. You can draw this much amount of power. This is optimal according to him. Now I need to disintegrate the 2 plus 3j among all the distribution networks on my own. So I have to do my own optimization exercise, but I do not have to share that exercise with the operator in the higher level of hierarchy or any of that information. That is the only advantage.
Okay.
Okay, we've got one question in the chat, and then we've got a hand raised. So the question in the chat, suppose some customers has flexible loads of 100 kilowatts for 1 hour at some nodes of the test system. Load is not battery, then how will you consider it in the formulation?
Yes, flexible loads can be considered. I mean, the loads here have been, as you can see, this is where Pi, which is equal to PGI minus PDI. So PDI is assumed to be constant. Instead of assuming it to be constant, we can multiply it with a parameter, let's say K, and that will become a variable. And that can take care of the flexibility of loads. I hope I have answered your question, sir.
Oops.
Yeah. So yeah, just one question is, so how does your capability curve determination will vary with respect to the dynamic additions or dynamic additions I mean is dynamic addition of any DGs, because with the market it will vary within a like if it's like 15 minutes or an hour interval, so every hour interval it will vary.
Sure.
So how does your algorithm will take care of like from both the sides, not only the distribution side, like on the transmission side, because you're talking about both the interface point. So how does your algorithm will tackle those situations?
So as of now, this algorithm, I mean, it has not been modeled with respect to time. So there is no variable. We do not consider that. What we can do is essentially this, let's say this particular curve gives you the, if I'm sharing this whole curve, this gives the worst case possible situations that can happen when the loading level goes down to 0.6 or it can go up to 1.4. So in one particular optimization exercise, I cannot take care of the time aspect, the ramp and other dynamics. That is absolutely true as of now. But I can share these curves in advance so the operators can decide, depending on what the situation is, depending on what the loading is, whether the point will be static secure or not.
Yeah, got it. Yeah. So I think your approach is
So far
majorly
I
valid for like
understand.
various. Sorry, Ahmed, go ahead. Yeah.
Okay. Yeah. I think he did not use. Do you use the transmission side? I think he did not use transmission
No, sir.
side.
No, sir.
This is
No.
the capability curve or aggregated capability curve at transmission coupling point.
Absolutely.
Not
Yes.
for transmission side. Yeah.
No, sir.
This
No,
is for distribution side, right?
absolutely. Yes, sir. Yes.
Yeah.
Okay. Yeah. Still, still the case is like, how exactly he will be tackling the dynamics in the from the DG side. That's still a question.
I agree. Absolutely. Yes. That cannot be tackled by one single curve. All the best
Yeah.
what a system operator can do is share a family of such curves so that the transmission operator can decide himself depending on looking at the curves. Let's say this particular curve shows the flexibility available in the distribution network for DJ outputs varying from 0.1 to 1. So that is the best that can be done.
Yeah, agree. Yeah, completely agree. But looking at the future, so I don't think like we'll get these numbers at fixed well.
Absolutely.
So,
Yes.
yeah. So the statistic, it's very stochastic in nature in future. So
I'll try to incorporate that part.
yeah,
Absolutely.
not a problem. Yeah, thank you.
Actually, yeah, my comment actually is very good. I like this one because I think it's very helpful for the utility side. And also, if I know it may vary, but just like voltage stability, maybe if I have this curve, then I understand what is the health of my, let's say, system of the, not health of the, let's say, structure of my microgrid or of my distribution system. Yes, I like this one. Yeah, thank you very much. Yeah, I like it.
Thank you. Thank you very much, sir. Thank you.
All right, we have time for one more question. Any other questions?
Not a question though. I can say that how do we apply in terms like mini grids or micro, the nano grids or those things. So do you think we can scale it to that level, or how exactly we can do it? Just a basic question. It's not like a
Sure,
technical.
sir. I agree with you. It is possible, but as long as you consider a single phase network. If you consider a 3-phase network, I'm not sure how to get such particular curve because the phases will be unbalanced. For a microgrid, if it is
Yes.
assumed to be balanced, absolutely yes, this exercise can be replicated as it is. But if a 3-phase network is considered, some other modifications might be required.
It's more likely. Okay, yeah, we can take the like linearized forms or representation from the unbalanced point of view. Yeah, I think that has to be done.
Yes, maybe it's possible. I have no idea at this point of time.
No, good one. Yeah, thank you.
Thank you.
Yeah, one other quick question is, can these graphs help in stability analysis with this?
With respect to stability, we have only, actually these curves are for steady state analysis, so they may not necessarily help for stability. We have the only stability limit that we have considered is the delta limit across two ends of every branch, and we found that they are never hit. So essentially it may not necessarily help in any stability analysis.
Okay. Piyush, thank you so much for your talk. If you want to put your email in the chat. So before we finish tonight, or our early morning, our morning in India, I just wanted to remind everybody that in about 10 hours, we will have our next session number 2. So we'll continue some of the work in theme 6 on DSO and energy management, the part 2 part. And so we'll have 5 talks on Tuesday morning US time, Tuesday night India time. So you're welcome to join us for those talks. So, but we appreciate so far our great discussions and topics and those that were able to join us for session number 1. We do have 5 sessions, and let me, I'll put the link in real quick for the UI Assist for the whole list of things, so you can have those. But we welcome you to participate in all 5 of our sessions that we'll have over the next couple days. So here is the link if you are interested to find the particular sessions, all the different sessions. You can get that particular link. So for those in the US, so we wish you good night. And for those in India, we hope you have a great day, and we'll see you